session of the last day of this very exciting workshop. It's my great pleasure to introduce Frank den Hollander, or Frank den Hollander, as we would say. Frank is from Leiden, and he will be talking about large deviation principles for the spectral radius of inhomogeneous Erd-H random graphs. Please go ahead, Frank.
Thank you, Renko. What a pleasure to be at this workshop, and this talk is going to be very much about graphons. I'm going to talk about an LDP that Darren Sen wrote down for inhomogeneous dense Erd-H random graphs, and I'm going to use that to study the spectral radius of two matrices associated with an inhomogeneous Erd-H random graph. So that is what this talk is about, and there's three parts. I'm first going to spend time on recalling for you what this LDP for graphons is in an inhomogeneous setting, and then I'm going to apply it essentially using the contraction principle, but that is easy I'm going to use it for adjacency matrix and Laplacian matrix. The adjacency matrix is easier to deal with than the Laplacian matrix, and you'll see where some of the problems come from in the Laplacian matrix case, and we're going to derive an LDP for the spectral radius of these two matrices, and then are going to go into what the rate function associated with these two LDPs is and what we are able to prove about them, what we're not able to prove about them, and this will in the end go and lead to some open problems. And this is joint work with four people: Arijit Chakrabarti from ISI Kolkata, Rajat Hazra, who is in Leiden, Martin Markring is currently a PhD student in Cambridge, and Matthias Fragar is doing a postdoc in Stockholm at the moment. So that's the program for this talk. And I'm going to first talk about this LDP for inhomogeneous Erd-H random graph, and I can immediately skip the first page because this is just telling you what graphons are and that there's a graphon, there's a cut metric, so I can immediately skip that. The only symbol I want you to remember is this phi, which is this measure-preserving bijective map that you need to go to the equivalence classes of graphons, and this has to do with the relabeling of your vertices, and that's the only thing that I will need you to remember for later, and the rest is all standard stuff that you have a twiddle space and this cut metric, fine. Now, the setting that we are going to look at is that we're going to pick a reference graphon, and we want to know a little bit about this graphon. We want that both the logarithm of this reference graphon and the logarithm of one of this reference graphon are integrable. So we do not need the graphon to be bounded away from 0 or 1, but when they get close to 0, close to 1, that they have to be sort of integrable in a logarithmic sense. And then what we're going to do is you say, this is a key given object, and then you're going to approximate this graphon by an n by n block graphon, and you have to do it in such a way that this will converge in L1 to your reference graphon. This reference graphon is fixed forever. And then what you're going to do is that once you have this block graphon, which is a good approximation of your reference graphon that you've picked at the beginning, you're going to construct an inhomogeneous Erd-H random graph by saying I have n vertices, and I'm going to connect vertex I with vertex j with a probability that's given by Rn of I over n j over n. So a vertex has a label, and then I over n is a number between 0 and 1, and you're going to connect these two vertices with that probability, and this will give you a dense but inhomogeneous Erd-H random graph, and as you let n go to infinity, this will start to, of course, look more and more like your reference graphon that you've picked, and this is how you're going to create a sequence of random graphs that will, in some sense, converge to your reference graphon. And you will need that similar conditions like this also apply to log Rn and log 1 minus Rn in order to be okay with this condition here. So I have defined now a sequence of dense inhomogeneous Erdős-Rényi random graphs, and I want to understand what I can say about this this object. And with this graph, you associate an empirical graphon by simply saying vertices. I pick an x and a y, and I look at vertices with labels upper integer part nx and ny, and if they're connected, I put a 1, and if they're not connected, I put a 0. So this is the empirical graphon, which is an n by n block graphon that I associate with my random Erdős-Rényi random graph. Fine, and I'm going to use the twiddle symbol when I want to talk about the law of the equivalence class associated with this empirical graphon, because we need to be working in this space W twiddle. So this is the model that I've set up, and now we're going to ask some questions about it. Now, the homogeneous LDP by Chatterjee and Vardan was generalized by Dara and Sen to an LDP that says, okay, if I look at this sequence of probability measures of the empirical graphons, this satisfies an LDP on our graphon space of the equivalence classes, and it has a rate n choose 2. Well, fair enough. Of course, that's also the rate that appears in the homogeneous setting. And there's a rate function that you get by taking the rate function as you see it in the Chatterjee-Vardan theorem, except you're going to now not put a constant here, but you're going to put your reference graphon here. And here is the graphon where the LDP says, well, what's the probability that I'm close to that graphon? And here is just an integral over the relative entropy with parameters r, x, y, and h, x, y. And this is your rate function, and then you're supposed to minimize over all the equivalence h that you get. And so here's this phi of this measurable by bijective transformation, and that is going to be your rate function in the space W twiddle with the countermetric. And so it's a generalization of the homogeneous case, and there are the technical issues involved, because you need to do approximations. How general can you make this reference graphon and stuff like that? And in the end, this came out. Maarten Markring picked up on this paper, and there were a number of things that could be slightly tweaked to include as general as possible ours. But this is our workhorse. And so this is the theorem that describes the large deviation principle of my inhomogeneous Erdős-Rényi random graph in the space of graphons. And that's well understood. And now we're going to try and do something with this. Namely, we're going to apply this to study the spectral radius of the adjacency matrix of my graph Gn, and also the Laplacian matrix of Gn. Okay, now in order to do that, I need to quickly remind you of some very basic stuff. Given a graphon, there is this linear integral operator, which we call a Graphon operator associated with your Graphon H, and this has an L2 norm, and that is an object that we need. And this object is well behaved, and that has been looked at in great detail in standard theory. And this is also very much L2 theory of operators coming from Graphon theory. So nothing fancy, but this is the norm of this Graphon operator. So every Graphon has an operator associated with it, and it has a norm. And this object will be important for us. Basic facts are the following. any graphon you pick, this is a self-adjoint bounded and continuous operator. It has a maximal eigenvalue and associated eigenfunctions that are all strictly positive, unless of course H is equal to 0, but we are not allowing for that. And then there is a maximal, and actually this norm is also the maximal eigenvalue of this operator. So this is all basic operator theory, and we need this in order to.
So you just interjected, you're not allowing it. So H has to be strictly positive.
Well, no, actually, we started with a reference graphon of which we do want some integrabilities near 0, but the reference graphon will not be able to hit 0, but it can get close to 0, but it has to do so in a certain integrable manner. That's all.
Question.
Okay. So let's go.
Question.
Yeah.
So does that condition already imply irreducibility of the operator?
Sorry, say that again.
So the integral condition that you have, does that imply the operator is irreducible?
I think it does.
Okay.
Yeah. So we're going to go to the first LDP, and this LDP says, let lambda n be the maximal eigenvalue of the adjacency matrix for finite n of my graph that I get by doing this approximation. And let's call P
Frank,
star.
sorry, but
Yeah.
so it's not only that it implies irreducibility, but for example, it doesn't allow bipartite graphons, right? Where you have 0 on a block.
I mean, I take a reference graphon. This reference graphon has to satisfy a certain condition. Otherwise, I cannot do the
Right, and it in particular, the condition implies it can't be, for example, a bipartite random graph.
Yeah, correct. Okay, so let P and star be the law of the largest eigenvalue of the adjacency matrix of the finite graph that I generate using the Rn, which approximates my reference graphon R. And here's an LDP that is an immediate consequence of the Darasen theorem and the contraction principle. It says this largest eigenvalue divided by n will satisfy an LDP on the real numbers with rate n choose 2. And there will be a rate function that you obtain by just saying this is the rate function in the Darasen LDP, and you need to minimize this over all choices of H twiddle in your graphon space W twiddle, that whose norm is equal to beta, right? And then since this has this was an infimum over I, you can just say that this now becomes an infimum over the W space rather than the W twiddle space, and the reason is that this operator norm is invariant under you applying a bijection to your H. And therefore, you have a formula here. Now, this is really in the space of graphons. You don't have to worry about the equivalence classes anymore. And you're supposed to take the rate function in the Darasen LDP and minimize it under all those for subject to the condition that the operator norm of the graphon H is equal to beta. And it's essentially easy. It follows from the theorem, the LDP graphon and the contraction principle. Plus the fact that there are certain nice continuity properties of this operator. And later when we go to looking at the largest eigenvalue of the Laplacian matrix, we'll see that there's some trouble coming up there. But here, everything for the adjacency matrix is still okay. So we have here.
Do you know what the optimal H looks like as a function?
I'm going to say something about it. We're now going to say, well, what are we able to say about this rate function? I'm going to draw a picture on the next slide. Well, we're going to need a constant, which is the operator norm of my reference graphon. And that number is important because if you would pick your beta, so this LDP says what happens when this lambda n over n is close to beta. Well, if that beta is the operator norm, then actually the solution is just H being equal to R. There's no large deviation, and that's your 0. And perhaps I should first show this picture. So the LDP says, I'm writing it in an informal way, the probability that lambda n over n is close to beta is approximately e to the minus the n choose 2, that's the rate. And here is my rate function. And this rate function sort of qualitatively looks like this picture. It has a unique 0 at beta being the operator norm of the graphon R, which is the reference graphon. And when you want to pick beta that, then you're talking about typical behavior. So that corresponds to a 0 of your rate function. And it means typically lambda n over n is going to be close to that number. And this curve is telling you what this rate function is when you are away from that point. And it has this shape. And let me state what we know about this kernel, sorry, what we know about this rate function in a theorem. We know we can prove that it's continuous and that it's unimodal. We can prove that it has a unique 0 at CR. So these are the kind of things that you always expect and hope to be able to prove. We can also prove that the curve is strictly monotone on either side of CR, so strictly decreasing on the left and strictly increasing on the right. And also in the space of equivalence classes, this variational formula has solutions, and this set is non-empty and compact in that space. So we know that the solutions are there and they're compact, but in general, it is not easy to say much about what these minimizers would be, and consequently about what this curve is. So at this point, you say actually saying more about this curve is a bit elusive, right? Okay, so that's the story. There is an LDP for the spectral radius of the adjacency matrix, and we have some control of what the rate function looks like.
And the fact that it's bounded at 0 is related to the integrability of log of R.
Exactly.
And the fact that it's bounded at 1.
Absolutely,
is,
exactly.
Okay. That's if and only if, probably.
Yeah. And the other values are simply not possible. Okay, now can we say something more about what the rate function actually is, well, and how what the minimizer is in some subcases? And we looked at the case where the reference graphon is rank 1. And of course, this is a celebrated choice. And we're going to make life a little easier for ourselves and say, okay, let this nu now actually be bounded away from 0 and 1 in order not to get into further details. Yes, we can say a lot, and all that we need to know is we need to know the first 4 moments of this function that is a function from 0, 1 to 0, 1. Of course, it has to be measurable. And it's in the rank 1 case, it's a little exercise to show that this norm of the operator associated with the reference graphon is just the second moment. And there is a further number that plays a role in what I'm going to say in a second, and that is this particular integral. I'm sorry, this should have been with respect to nu r. There's something missing here, nu dr. I'm sorry about that. And so this will be the difference between the square of the third moment of nu and the square of the fourth moment of nu. This is a positive number because this nu is between 0 and 1. And so there are numbers in terms of the first 4 moments of the nu function. And the theorem making a more precise statement. Yeah.
What do you mean by rank 1 operator is like
a rank 1 operator is that my reference graphon is a product. That's here. And for some nu.
But it also means that it's a rank 1 operator.
Yeah. Yeah.
It has one non-zero eigenvalue and all the other ones are 0.
Right. And in terms of this function, you have 4 moments, and then the answer is that if you are looking at near the zero, you will see the usual quadratic behavior, and the constant is computable in terms of these three moments. And we have also information, coming back to your question, Remco, any H that is a minimizer is up to this equivalence given by, it's very close to R, of course, because you're very close to the minimum. And if you're at CR, then your minimizer is R. It is a perturbation of R, and the perturbation is linear in the distance between beta minus CR. So we're close to CR with beta, either on the left or on the right. And there's a certain shape with which you will perturb this your rank 1 reference graphon. And so there's a precise description of what your graphon will look like. Any minimizer will look like if you are close to the minimum. Yeah.
Do you expect that for beta close to CR, there will be a unique minimizer?
We certainly know that to linear order, this is the unique shape.
Right.
But there could be higher order perturbations where things are not unique, but certainly to leading order in the approximation, the perturbation is unique. Yeah.
But would you expect it to be linear? You do the mic, sir.
But this still raises the question whether you would, I mean, you may not be able to prove it mathematically, but would you expect it to be unique or not?
I don't know. I have no idea. It might be, I would expect it to be unique, but I don't know how to prove that.
So if I am looking at from a graph theoretic point of view, so what is the entropy minimizing graph? How does it look like?
It looks like, so if apart from the equivalence class, it says it looks like R plus beta minus CR times this object. And this object depends on your reference graphon. And apart from the equivalence classes, that's the solution.
But is there interpretation like in terms of clicks or something that comes up in triangle counts?
No,
Okay,
because my reference graphon is assumed to be positive everywhere. It's in fact rank 1 and more, and then this is never going to sort of accumulate or anything or have singularities. I don't see that. So this is the formula.
So in particular, it's polynomial in R. Would you believe that to be true beyond the rank 1 setting?
No, I would not believe that to be true. I'm going to make some remarks about that. Very interesting and good questions. Now, first of all, it remains open whether my rate function is convex. In many cases, rate functions are convex. In many cases, they're not. We have no idea how to prove that here. The dependence on beta is complicated. We do not a priori expect that this function would be analytic function in beta, because there could easily be bifurcations occurring as I vary beta in the solution. You know, maybe yes, maybe no. We just don't know, and it's naive to expect that this would not happen. I mean, if you remember the pictures that Charles put up on Monday in this edge triangle model, okay, it's a different story, but then you know, things can be very complicated, and one should not a priori sort of say, oh, this will be okay, but we don't know. Now, the scaling corrections are not rank 1. So even though you start with a rank 1 matrix, this is not rank 1. So the moment you move away from your minimum, you lose already immediately the rank 1 property. And this curvature that we found here, so how does your rate function behave? It behaves quadratically with a certain curvature, and that fits nicely with the CLT that that was proved around about the same time for this large spectral radius of the largest eigenvalue. And so the fact that the variance and this thing match up, that's part of the folklore of large deviation theory. Large deviation theory does not apply the central limit theorem, so it's not for free, but very often these things match up. And in this case, things are also matching up. So life is halfway decent at the minimum.
Sometimes you can also conclude the central limit theorem from the large deviation principle and
Yeah,
the
but-
double derivative.
Yeah, but you need to do more. You
Mhm.
actually need to go a little bit in the complex plane. So whereas the law of large numbers is immediate from LDP, CLTs are not. You need a little extra work, but very often they fit. But we will see for the Laplacian matrix, no, something else is happening. Now, so this sort of concludes the story for the spectral radius of the adjacency matrix. Yeah, you can go beyond rank 1, you can go to finite rank. There's still things you can do, but the story does remain that it's not easy to get detailed properties of what this rate function really, what its properties are as a function of beta.
So I was wondering what if instead you would allow a simple sort of rank 1 analog for bipartite graphon, and then looked instead of the largest eigenvalue at the smallest, which would be sort of a nice analog there. Could these techniques be generalized to that?
Maybe. I would need to think about that, but that's certainly an interesting question. I mean, there is a lot of flexibility in what we're doing, but there are also some hurdles and so perhaps, but it's certainly a good idea. But I would not sort of immediately bet on this and say I know how to do this by tomorrow morning. No.
Even more difficult would be the directed case, right?
Yes.
Because then your operator is no longer self-adjoint. That's a disaster.
That's a disaster. Okay, so in the remaining time, I'm going to focus on what happens when we do not look at the adjacency matrix, but at the Laplacian matrix. And the Laplacian matrix is that you take a diagonal matrix, which is whose elements are the degrees of the vertices, and you subtract the adjacency matrix from it. And this object is sort of interesting when you want to start to run a random walk on your graph Gn, because then the spectrum of this operator is going to tell you something about mixing times. But we're going to look at this as just an operator in itself and say, well, what about the largest eigenvalue of this operator? And can we derive an LDP for this? And that's what the second LDP that I'm going to tell you about will be. And it turns out that this Laplacian matrix poses new challenges because it is in many respects a somewhat more delicate object than the adjacency matrix. And that's partly because this operator, even though it's very simple, is not sort of living, and how shall I put it? It's not sort of quite living in the same world as the AN does. And in fact, what we're going to see is that there is now going to be a difference between deviations upwards and downwards because they're going to live on different scales. They have different costs, which is not what was happening for the adjacency matrix because the cost was always n choose 2. No matter whether you were moving up or whether you were moving down. And so now there's going to be 2 LDPs, one on the right and one on the left, and I want to tell you about those. And the Laplacian operator lacks certain continuity properties that make this analysis more difficult. I have put here in progress because there are still, 2 small technical things that we're sort of worrying about that have to deal with this. And so it's not completely done yet. There is some struggle here going on, which I will not go into the technical details of that. But here is what we are having. Again, to formulate things, I need to talk about Graphon operators. There is a degree function that says you pick an x and you just integrate your Graphon over y, then that will correspond to the degree associated in the limit with the point x. There is a degree operator associated with that, which is very simple because this is a multiplication operator. And then the Laplacian operator would be the operator that I had before. This is going to be my degree operator because if I integrate out over y and this ux doesn't depend on y, I get dxy. So I just get this beginning part is that operator, and the other one is the old operator that I had, which was the operator associated with my Graphon. So I'm dealing now with a different operator, which is a difference of two operators, the degree operator and the operator that I had before, the Graphon operator. And this operator is not as well behaved because, for instance, if you have a sequence of Graphons that converges to a limiting Graphon, the eigenvalues and eigenvectors of this Laplacian operator at that sequence may not converge to the limit. So there's a lack of continuity properties here that we did not have for the adjacency matrix. Okay, let me again introduce the L2 norm of this object, and let's see what we are able to show. Well, this is certainly a bounded operator. We know that it's lower semi-continuous in H. It's not continuous. In fact, if you look at star graphs, then you're going to see that you're going to have discontinuities there. And I'm going to introduce a number, which is the norm of that more complicated operator now, the Laplacian operator. And we're going to call this C hat R. And the C hat R plays the complete analog role of the CR that we had before, which was the norm of the Graphon operator. And this should be the zero of a rate function. And in fact, we have a downward LDP. So we're going to look at what is the maximal eigenvalue of this Laplacian operator divided by n. It has a law Pn star. And it turns out that there's a downward LDP with rate n choose 2 and with a rate function that is of the type we had before. You take the infimum of the Darasen rate function and you normalize, you put as a constraint that the Laplace operator of that h is less than or equal to beta. And the downward LDP is the statement that this, it says the probability that your largest eigenvalue for your Laplacian matrix divided by n is less than or equal to beta is going to decay with a certain rate function. And since we're looking at the downward rate function, it is we're talking about a function here that looks at the left piece, and it says if you want to be below something that is below this number, you're going to pay some cost, and the function looks like that. And again, we are able to prove some very general properties about this rate function, and we're also able to show that there is the minimizer of that variational formula defining your rate function is non-empty, and it is compact in the W twiddle space. And so all is good. And we have found a picture on the left. So if you say, if your largest eigenvalue of Laplacian matrix wants to be smaller than what its typical value would be, you pay on the scale n choose 2. And okay, now we're able to say a bit more about what is happening near the zero. If we're assuming that the reference Graphon is positive definite, which is more general than rank 1, then we're able to say more. And what we do is we're going to introduce a kind of tilt of my reference graphon. Think of this as a kind of brother of the Camer transformation as you do it, a little bit like that, but now in the world of graphons. And you're going to tilt it by a function that depends on x. And you have to choose this tilt. This tilt plays the role of a Lagrange multiplier such that the function, the tilted function, achieves the minimum beta. So I'm sort of tilting my graphon, my reference graphon, such that the deviation of beta now becomes the typical value for this tilted reference graphon. So that's very much in the spirit of how you prove Camer's theorem. And
is this theta unique?
Theta is unique. Yeah, yeah, because you can. It is. Yeah. And then in that case, you can find out what the zero of your rate function is. It's just the supremum norm of your degree function. And what we find is that we have a more simple representation for the rate function, and it is an infimum over a certain set where the degree has to be larger than the beta. So there's a certain representation in terms of the function that I introduced. You have to integrate it over a certain set. And if you see what my rate function is doing as it approaches, it's zero, but it's approaching it now from the left because I'm only having a downward LDP. There is a quadratic term, but there is a term that depends on what the degree function is doing near its maximum. And this is going to vanish as beta goes to c hat. So you're not going to get quadratic behavior. You're going to get behavior that is below quadratic. And the way it is below quadratic depends very much on what the degree function is associated with your reference graphon and how it is sort of behaving near its maximal value. And there are various scenarios possible, but the main message is you go to zero faster than quadratic. So it's not standard CLT.
Question.
Yep.
So for this measure of SR beta to be zero, do you still need the fact that R is positive definite, or just the fact that this is zero does not need?
No, yeah. For the theorem, you need that it's positive definite, and to get this representation, and then you note afterwards that the positive definiteness will also give you this bound. Right. So you're right. So you're right. I do need it everywhere.
I see.
Yeah.
I see. Okay.
Very good.
Thank you.
Okay, I'm moving 2 more slides to go. There's also an upward LDP. The upward LDP has a rate function that you can again write down. And this upward LDP, however, lives at rate n, not n rate 2, choose 2. So it is cheaper to make upward large deviation than it is to make downward large deviations. And the rate function is quadratic, and there's some constant here which we think we know, but we haven't really proved that yet. So I'm being more rough here because we haven't really proved. So this picture looks like the other picture at the other side, except the rate is now n and not n choose 2. So deviations in the upward direction for the Laplacian matrix are cheaper than downward large deviations. And for the adjacency matrix, it was the same on both sides. And
are you basically changing one row and column?
Something
Also
like that.
n?
In fact, it turns out that somehow in the whole story here, the maximum degree, the large deviation of the maximum degree is somehow dominating the story. And so I'm coming, this is my last slide. So there is an upward and a downward LDP. They have different rates. To get your hands on what these rate functions are exactly doing as a function of beta remains a bit elusive. We have obtained some properties of them, and again, are they convex? We don't know. Should we expect them to be analytic? I doubt it, but these questions remain open. It also remains open when you want to go beyond the positive definite case, because then things become a bit more tricky with this Laplacian operator. And thirdly, there is no central limit theorem known for this object, and that probably is related to the fact that we have different rate functions on the left and on the right, and on the left things are less than quadratic, on the right they are quadratic, and so there's an asymmetry here, and that must mean that if you are trying to get something central limit theorem like for this object, it's going to be a more difficult story. It simply has not been done, and we don't know what to do.
And it might not be true.
And it might not be true. So, but that's an enigmatic question. So the rest is all up in the clouds. Christian's question is very relevant. And you could, of course, say, well, what about the second largest eigenvalue? I mean, the sky is the limit. Thank you very much.
All right. Any further questions? Yes.
So I guess, Frank, so I guess one maybe the more substantial question is, in the sparse regime.
Yeah.
So in the sparse regime, if you look at the empirical spectral distribution, it's sort of known because of this beautiful work of Charles Bourdenave and Sales, that it depends on the local properties of the graph, like local weak convergence.
Yeah.
And then there are these, so then you can ask what about large deviations for the empirical spectral distribution?
Yeah.
And then now there's like this, cool work of like Bourdenave and Caputo about like local, large deviations for local weak convergence. Yeah. So do you think some of this stuff can be extended to the sparse regime, not the maximal eigenvalue, but like the spectral
I don't think it can be extended because you really need different tools. I say what we've done here, you're all building it on Graphon theory. So I don't know that, of course, there's this intermediate regime interpolating all the way between sparse and dense, where at the level of the spectral distribution, we know a lot, and you get interesting things that have to do with, bigness semicircle laws. But for the largest eigenvalue, this is not clear. And I think it will really require these other techniques to make hopeful. I don't think that this has much to say about that problem.
Right, I guess not the maximal, but like if you look at the empirical spectral distribution, then
it may be, because that's a much easier object. For instance, we know where that scales to in the whole range between sparse and dense, and then large deviations would be an interesting thing to do. But that's a calculation also. You get into all this quantum, free probability combinatorics and stuff like that. Okay. So I don't know the answer, but that's certainly an interesting thing to look at.
Okay, and one minor question. I mean, suppose you look at an exponential random graph model, which we know converges to some sort of graphons under appropriate spaces, appropriate conditions, and then you ask, now you want to condition exponential random graph model to have a weird, whatever spectral property. Okay. Can your techniques extend there?
There, I think one should be able to do something. I mean, if you would be tilting by your largest eigenvalue, then this is going to certainly, in the dense case, is going to help you. Sure.
Thank you. I wonder, like, at some point I see you mentioned the cut metric for the Laplacian that generated from the Graphon. So I wonder how that is defined. I'm curious on the diagonal parts, how that would come into the definition of the cut metric.
I mean, the cut metric and the space is what it is. We're not changing anything. I'm just saying that the Laplace operator is lacking certain continuity properties that your adjacency matrix operator had. And those things are hitting you. And they're hitting you because most of your calculations you do in the space W rather than W twiddle. And so certain continuity properties make the proof harder. And that's all. What I mean, the space is what it is.
So the cut metric the cut metric.
No, the cut norm is what it was before.
Okay.
I'm not changing that. I'm just saying that the operator is less well behaved, and that's something we really need to struggle with.
So it's well known from spectral graph theory that instead of looking at the Laplacian, looking at the normalized Laplacian, where you multiply with the square root of L, is nicer behaved, it's nearer to the Cheeger constant and things like that. So would you expect that the normalized Laplacian has a two-sided LDP maybe?
Maybe. I mean,
Or do you
you're right
think
that makes life easier. We actually haven't done that. We haven't really thought about that. Yeah, that would be nice to look at, and possibly this makes some of our trouble disappear. So it would be good to consider that. But I'm not. I mean, we haven't done that yet. It's another good suggestion of what to look at.
A final question?
Whoa.
Yeah, a final question. Very good.
So out of curiosity, your notion of relative entropy here, the pointwise average, do you know whether that has a reasonable duality, like a Don-Skavaradan representation where you maybe soup over subgraphs or something like that?
Yeah, but I don't see what that dual representation would do for us here. Of course, you can write relative entropy as again in a kind of variational form, but we haven't been able to use that. We were just computing head-on with this expression, and putting a variational thing in between is only going to make life harder, I think. But I don't know whether it might be useful at some point.
All right, I propose that we thank Frank for his beautiful talk. And it's my pleasure to introduce Kavita Ramanan, who's the second